Alright, so we have yet another question about estimation. So let me read the question. Suppose we have got 5 random variables, x1 to x5, and these are picked up from a normal population with variance sigma square, so they share the same variance. And we consider the following estimator for the sigma square, okay, the variance, which is s star square. This may not be really clear from here, but this is a star square given by 1 over n, sum from 1 to n, xi minus x bars, the whole thing squared, okay, where x bar in this case is the average of these random variables. So first question says show that x star square is a biased estimator of the variance sigma square, and estimate the amount of bias when a star square is used to estimate the sigma square. Okay, so it's pretty simple question, as long as we remember, of course, the following. If I define S square to be the sum from 1 to n, these random variables xi's or x bar square, over, instead of n, let us define this s square to be with n minus 1 in the denominator. Okay, so if in this case, if I define some random variable s square, then we can easily show that n minus 1 s square over sigma square is chi square distributed, okay, with n minus 1 degrees of freedom. All right, so that's one of the things that we recognize, okay, and this can easily be shown, but without recognition of this fact here, we wouldn't be able to move forward with this question. After identifying this relationship, okay, this is distributed, by the way, okay, at identification of this, we realize that chi square distribution is related to this random variables, this random variable is square, and we also know that chi square has certainly a simple mean value. Okay, it is mean value, it's equal to its degrees of freedom. So the mean value of this chi square is actually equal to its mean. Its degrees of freedom, which is n minus 1. So therefore, if I look at the expected value of n minus 1 s square over sigma square, I can definitely say its mean value, since it's chi square, is n minus 1. Okay, and therefore we can easily see, because there's the only difference between this random variable s star square and s square is this change in the denominator, which is n here and it's n minus 1 in here. So therefore the relationship between them is pretty simple. S star square is equal to n minus 1 s square over n, right? So it's a pretty simple relationship, and using this relationship I can actually calculate the expected value of s star square, similar to by using this fact and this fact. Okay, so you can actually calculate this pretty easily to be sigma square over n and n minus 1, and you can see that n and n minus 1, this is the difference right here. Okay, due to n being the denominator in here and n minus 1 being the denominator in here for s square. So therefore we have actually identified the expected value of s star square to be sigma square over n and n minus 1. In other words, in always repeating sampling, s star square values tend to center around the value slightly lower, right? Because this is strictly lower for positive values of n, lower than sigma square itself. So therefore they tend to center around the value slightly lower than the sigma square, the original value, the variances of these normal population, and namely this is the result. So therefore we conclude that s star square is a biased estimator of sigma square, because it's not equal, it's smaller than, so it's underestimating it actually. All right, so that's the answer to the first question, that we basically demonstrated that s star square is a biased estimator of sigma square. Okay, The second question asks, estimate the amount of the bias when S star square is used to estimate the sigma square. The amount of bias for S star square is used to estimate sigma square is given by the following formula. Bias is given by expectation of S star square minus sigma square. Okay, that is the definition of the bias, the difference, which is given by n minus 1 over n sigma square minus sigma square, which is given by 1 minus 1 over n sigma square. Because sigma square is a positive value, right, the negative bias here indicates that S star square is thematically underestimates this sigma square. Okay, that's what that means, and as n goes to infinity, okay, if n is larger and larger, tends to larger and larger values, then you can see that the bias becomes smaller and smaller, and at the end, if n goes to infinity, the bias becomes 0, so there would be no difference between S square and S star square in terms of estimating the sigma square. So we also note that S star square defined with n minus 1 instead of n in the denominator is an unbiased estimator of sigma square, and therefore is more commonly used to estimate sigma square than S star square. Okay, so it's also commonly referred as the sample variance. Okay, so instead of using S star square, we use S square, okay, to estimate the variance. Okay, and that is also known as the sample variance because it becomes an unbiased estimator of the sigma square.